So we'll look now at another family of equations, those related to exponents and logarithms. So what we'll do is we'll start by reviewing some of the basic properties of both of these and then look at a handful of equation examples. So let's start with exponentials, right? So just to recall, these are things like 2 to the x, so examples, 2 to the x, 3 to the x, even something like 2 to the negative x. And then I'll bring up now an important example called e to the x. So e is a special number that's approximately 2.71. It's called Euler's constant. And it's sort of one of those special numbers in mathematics that seems to appear in many different contexts. It appears naturally in calculus in particular. Comes up just sort of in many different situations, sort of unexpectedly. It is a very complicated number, sort of like pi. In our very last module, we'll discuss rational and irrational numbers. E is an example of an irrational number. It's actually even more complicated. It's what's called a transcendental number. So I'll say it is infinite, and it is transcendental, which is definitely not a topic covered on this exam, but it is sort of interesting to know, I think. And I'll say it's transcendental like pi. But it's often used as the base of exponentials. It just seems to come up in many different ways. Okay, so you should certainly be familiar with, if you see e to the x, what they mean is an exponential formula where the base is like 2.71 approximately, though this decimal does go on forever and never repeats. Okay, so let's look at a few basic properties of exponentials. Of course, some of the most important are how addition in the exponent works. So it says if I have two things I'm adding in the exponent, this splits as a product on the outside. So for example, 2 to the 3 plus 1 is equal to 2 to the 3 times 2 to the 1. So 8 times 2, so 16. Okay, I mean, of course, you may have just known that 2 to the 4 was equal to 16. Okay, but this basically gives us a general way to say if I have addition in the exponent, it comes outside as multiplication. Now I have to ask, okay, what happens if I have multiplication outside? What if I have a to the x times b to the x? Well, as long as this x is the same for both of these, I can multiply the bases. Okay, so for example, 2 to the x times 3 to the x is equal to 2 times 3 to the x, so 6 to the x. Something else we can look at is what's called iterating exponentiation, where I have a to the x and then I raise it to the yth power. What does this do? I call this iterated exponents because first I hit a with x in the exponent, and then I hit it with y. So what's this like? Well, it turns out it's the same as just exponentiating one time, but what you exponentiate is x times y. Right? So this is equal to a to the power x times y. So for example, if I have 2 squared to the third, this is the same as 2 to the 2 times 3, so 2 to the 6th. Okay, so that's the kind of example you maybe want to keep in your mind. And then one sort of basic foundational point, which is anything raised to the 0th power is 1 by convention. Okay, so that's this here. Right. So we can look now at the inverse of exponentials. We can look at logarithms, which have very related rules. And in fact, one can prove the rules for logarithms just using the rules for exponentials. Right, so let's just recall what a logarithm stands for. So if I have y equals log base a of x, this is shorthand and equivalent to a to the y equals x. Okay? So a is called the base of the logarithm. And you can, in general, pick any positive number to be the base, but certain logarithms are more common than others. Certain choices of bases are very, very common. Some natural ones include 2. This is very common in computer science because you have binary notation for numbers, so 2 is very natural for this. So we'll say so common bases. A equals 2, so we get the log base 2. Another common one is 10, so you get log base 10. Sometimes this one is written without a base. They just write log. Okay? That's because 10 is the base of our number system. Right? We go with ones, then tens, then hundreds, then thousands. So 10 is somehow universal to the way that we Westerners write numbers. Okay, so we call this sometimes the common logarithm. And then the other one that's kind of strange if you're not familiar with it is, again, this number e. So if I take a to be e, so approximately 2.71, then I can talk about the log base e. This gets a special name. It gets ln for natural logarithm. So these are the 3 you're most likely to see. Base 2 because of its applications to computer science, base 10 because of its connection to our number system, and then the natural logarithm base e just because of e's pervasiveness in mathematics. Okay, so let's look at the formula. They're very related to the exponential formulas. Here it says, okay, if I have a product of things that I'm taking the log of, it splits as a sum outside. So, for example, log base 10 of 20 times 10 is equal to log base 10 of 20 plus log base 10 of 10. If I have a quotient here instead of a product, it works the same way, except I have a subtraction sign, and here I have an addition sign. If I have an exponential, right, so if I'm taking the logarithm of something like x to the power y, what's beautiful about logarithms is that power y comes down outside of the logarithm as a product. So this y comes down here, and I get y times log base a of x. And then we have a few sort of foundational points. Log base a of 1 is 0, and log base a of a this is not 0, it should be equal to 1. Okay, so these are just a few kind of basic building blocks to play with logarithms and exponentials. So now that we've sort of gone through the mathematical theory briefly, let's look at a few examples and try and apply these tricks and rules to solving equations. So here's one. We have an exponential equation. 3 to the power x squared minus 1 should be equal to 1. Okay? I think this is very, very difficult to try and just guess your way to the solution. Okay? What we want to do is use our properties of logarithms and exponentials to solve this. So recall that logarithms and exponentials undo each other. So to solve this equation, what I'm going to do is hit both sides with an appropriately chosen logarithm. My exponential is 3, so I'll hit it with log base 3. So let's take a look here. So I'll say this is log base 3 of 3x squared minus 1 equals log base 3 of 1. Okay? So what is happening on the left-hand side? Well, the log base 3 is going to kill that exponential. So I'll just get x squared minus 1 on the left-hand side. How about on the right? I need to identify log base 3 of 1. Well, this is 0, right? Because log base a of 1 equals 0 for all a. Okay. And now I just have to solve this. So you can solve this with the quadratic formula if you wanted to. You could also do what's called factoring and write this as x plus 1 times x minus 1 equals 0, and determine that x equals minus 1 or 1 are my solutions. And we can check this. If I plug in x equals 1 into the original equation, I get 3 to the 1 squared minus 1, so 3 to the 0, which is 1, as desired. And then same with minus 1. If I plug it in, I'll get 1 on the left-hand side. So here the key trick was to use logarithms. Let's look at a similar equation. So here I have an exponential of 2. So instead of taking log base 3, I'll take log base 2. And a similar thing will happen. The exponential on the left-hand side will disappear, and I'll be able to solve a more simple equation. So we'll say log base 2 of 2 raised to the power 2x minus 3 equals log base 2 of 1/4. On the left-hand side, well, the reason I took log base 2 was to kill off the exponential. So I just get 2x minus 3. On the right-hand side, how do I deal with this? Well, I think the easiest thing to do is split this up as a quotient, right? So this is log base 2 of 1 minus log base 2 of 4. Okay? So I have 2x minus 3 here. Now, what is log base 2 of 1? Well, log base anything of 1 is big goose egg, 0. And now all I have to really do is figure out what is log base 2 of 4. Okay? So one way to do this is to write 4 as 2 to the power 2. The 0 goes away. And I can bring down that power 2. Right? So here I use the fact that log of base a of x to the y equals y times log base a of x. So the power inside can come down. And last, I observed that log base 2 of 2 is 1. So I just get minus 2. Right? This is the fact that log base a of a is always 1. So now I just have a very simple linear equation that I have to solve. Right? So what is this equal to? Take the 3 to the other side and get 2x equals 1. So x should be equal to 1/2. Right? And does this make sense? If I plug it back into the original equation, I get 2 to the 1 minus 3, so minus 2. 2 to the minus 2 equals 1/4. Sure, right? The minus sign, the exponential, puts it in the denominator, and then I square 2 to get 4. So I get 1/4. Very good. So let's look at equations that are based around logarithms, not exponentials. So what we just looked at was I have an exponential equation. I solved it by taking logarithms. Here I'm going to take logarithmic equations and solve them by taking exponentials. Okay, right? I mean, they undo each other. So if I encounter one type of equation, logarithmic, I can solve it by using exponentials. So here I have log base 7. So what exponential am I going to use? 7. So I'll say to solve log base 7 of minus x plus 1 equals 2, I'll exponentiate both sides with a base of 7. So I'll say 7 to the power log base 7 of minus x plus 1 equals 7 squared. Right, so the left-hand side cleans up, and I just get minus x plus 1. And then we have to ask ourselves, what is 7 squared? This is one of those ones you kind of got to know. This is 49. And now I'm doing basic algebra. Right, so now I have minus x equals 48. So x is equal to minus 48. Right, so pretty straightforward. I kill off the logarithm by exponentiating, and then I do the algebra to solve. Let's look at one more. Okay, so here you have this weird ln thing, right? But don't be concerned. This is just a special logarithm. Okay, so just recall ln of x is just notation for log base e of x, where e is something like 2.71, but it's really this kind of Euler's constant. So you can think of it kind of as pi. It has this sort of decimal approximation, but in reality it's an infinitely long number. Now in our case, it won't matter so much. Right? So what we'll do to solve this is we'll exponentiate. So I'll say that e to the natural log of 2x plus 2 equals e to the 0. So the left-hand side cleans up as 2x plus 2. But you might say, James, I know nothing about e. I don't even have a good approximation for it. How am I going to solve e to the 0? Well, it doesn't matter what that base was. Anything to the 0th power is 1. Right? So it's sometimes nice to remember that a lot of the important things you'll need to know for this CLEP exam don't really involve number crunching so much. I mean, you will have a calculator and you may be asked to crunch numbers sometimes. But a lot of times it's more about basic principles. And here we have to identify that e to the 0 is just 1. I don't need to use my calculator. So I get 1 here. And again, now I'm solving a very simple algebra equation, and I get that x is equal to minus 1/2. So I took this nasty looking equation, and maybe I didn't even know what ln meant. All I have to do is remember the sort of fundamental properties of logarithms, which are they undo exponentials, and exponentials undo logarithms. And then multiplication and division sometimes split nicely, and then log of 1 is always 0. Any exponential to the 0th power is always 1. Using these foundational tools, we can solve a variety of equations.